Okay, so DI4. So yeah, this is just really a matter of keeping straight all the different formulas that go into defining xi, yi, xi star, all that kind of stuff. So we're computing the volume under the graph, blah, blah, blah. We're computing a double integral. And in other words, we want to compute this Riemann sum. We're going to approximate the Riemann sum by just throwing away the limit and calling it an approximation. Is that cool? Okay. And so we're going to have f xi star yj star delta a. And these things are going to be defined in terms of the domain. So let me draw a picture of the domain. Domain. Let's see. X goes from 1 to 5. And y goes from -2 to 6. So my rectangle is like this. So that's -2 and that's 6. Right? I'm going to chop that up into pieces with n equal to 4. Okay, so chopping with n equal to 4, I claim that I'm going to sort of be breaking it in the x direction at 2, 3, and 4. I mean, I've arranged it, by the way, where the arithmetic works out to be all integers just for convenience, right? So that's 2, 3, 4. And slicing in this direction, it's at 0, 2, and 4. So your delta y is equal to 2, and your delta x is equal to 1. Now you can get that from the formulas because delta x was b minus a over n. N was 4. A and b were 5 and 1, and so this gives you 1. Does that make sense? And likewise over here. Okay. Okay. So delta a, that's delta x times delta y, so that's equal to 1 times 2, so that's 2. Okay. Now, in the statement of the problem, they tell us that xi star, we're supposed to choose xi. Now, we were talking about this earlier in class. When you're doing approximations, yeah, it absolutely matters what xi star you pick. If you pick left endpoint or the right endpoint, you get different answers, different approximations. The problem here is telling us what to choose arbitrarily. Now, there's no reason why we have to. If we could totally choose xi star to be xi minus 1, the left endpoint. It would just give us a different approximation. Does that make sense?
So when we're saying that xi star equals xi, we're saying that we're going to be using 2, 3, 4, and 5?
Yep.
Okay.
Yep, that's right. Exactly. So let's write down the formulas now. So we have formulas for xi and yj. So xi is a plus I delta x. Now delta x is 1. A is also 1. So xi is 1 plus I. Make sense? So that means that for I being 1, 2, 3, and 4, my choices, my sample points, they call them, are 2, 3, 4, 5 because of that formula. Yeah, just like you said. Yeah. Okay, similarly then, for yj, well, yj is c plus I delta y, so that's -2 plus 2i, and so your y1, y2, y3, y4, these are 0, 2, 4, and 6. Oops, sorry, there we go. Good? Okay, so now we've got a summation. I'm kind of running out of space here. We've got this summation where both I and j are going to go from 1 to 4. And that means that we're going to have 16 terms here. In each case, we're going to be looking at f of, well, the corresponding x choice. In other words, whatever one of these, depending on which I you're looking at. And then the corresponding y choice, depending on which j you're looking at. And then you're going to be multiplying that by the area, which we've agreed is 2. So this is always 2. That's going to always be a constant, independent of I and j, which is handy. Right? So you just got to add up 16 things. And for each of these, basically you're going to be looking at 16 little rectangles. Here's your 16 rectangles. And for example, let's consider this rectangle here. For that rectangle, note that I is equal to 2, and j is equal to 3. So that means we're looking at x equals 3. I was equal to 2, so x is equal to 3. J was equal to 3, so y is equal to 4. Means we're looking at that point. We're looking at the upper right-hand corner. So that point, 3 comma 4, plug that into your function. Let's see the function. Here's the function. It's given right there. 10 plus 2x plus 5y. Plug in those values that we just agreed on. X was 3, y was 4. And that gives you a value of f, which you then multiply by 2, and that's one of your 16 summands.
So that's the volume in that square?
That's our estimate of the volume sitting over that square. That's right. Now, it's going to be a little off, right? It's an approximation, but yeah, that's right. Yep. And then when you add up overall 16, that's going to give you an approximation of the total volume. Yeah. So yeah, I mean, really what this problem is all about is just, like I like to say, getting your hands dirty and actually seeing how this construction computes what we claim that it computes.
I just had a lot of problems with the notation.
Yeah, no, absolutely. There's a lot of notation, and the very first time you tend to feel like a little lost in the notation, but it's important to realize that the notation just pretty much tells you exactly what to do if you just interpret it literally. Yeah. Yep. Is everybody happy with this problem? Any questions on this? Okay. Kill the recording.